Welcome to Ask and Learn.
So now we'll work on problem 20 from chapter 6. In this problem, we are asked, what is the frequency of radiation whose wavelength is 0.86 nanometers? So we need to remember the relationship between frequency and wavelength. So the speed of light is equal to frequency times wavelength. So wavelength, frequency, will be equal to the speed of light over wavelength. And we know the speed of light is equal to 2.998 times 10 to the 8th meter per second. And the wavelength is given in the problem as 0.86 nanometers, but we need to make sure that we account for the units here. So we're going to write 0.86 times 10 to the minus 9 meters. So we see that meters will cancel, and it gives us seconds to the minus 1, or hertz. So we have 3.5 when we do the calculation, times 10 to the 17th hertz. If we wanted to write this without scientific notation, we would have to write 350 petahertz. It's capital P for 10 to the 15th power. So for part B, we're asked, what is the wavelength of radiation that has a frequency of 6.4 times 10 to the 11th seconds minus 1? So here we need to do the reverse of what we did before. So we can say that lambda, or wavelength, is equal to the speed of light divided by nu, or frequency. And so the speed of light remains unchanged at 2.998 times 10 to the 8th meter per second. Frequency, which we're given, is 6.4 times 10 to the 11th seconds minus 1. And when we do this calculation, we get 4.68 times 10 to the minus 4 meters, or 468 micrometers. In part C, we're asked, would the radiations in part A or part B be detected by an X-ray detector? So X-ray detectors will detect photons or light radiations, which have a very, very high energy, very, very high frequency, and a very short wavelength. So we can see that A has a much higher frequency than B. So if one of them is to be detected, it would be the radiation from part A, because it has a much higher frequency. Now in part D, we are asked, what distance does electromagnetic radiation travel in 0.38 picoseconds? So here, we know the speed of light, so we just need to multiply by this time to see how far the light will go. So 2.998 times 10 to the 8th meters per second is the speed of light. And if we multiply by time, which in this case is 0.38 times 10 to the negative 12 seconds, the seconds will cancel. And we get 1.1 times 10 to the minus 4 meters or 110 micrometers. So this is radiation will travel 110 micrometers in 0.38 picoseconds.